What's up, everybody? Today we're going to be going over LeetCode problem 1482, minimum number of days to make M bouquets. So I'm trying to keep my video length down, so I'm going to try to explain this quickly and then get through the algorithm. So we're given three things. One is an array of integers, two, M is an integer, and the third thing, K, is also an integer. We need to pick adjacent flowers from the integer array such that we make M bouquets or M groups. Okay, and in the integer array, bloom day, the number in the array tells you the day at which that flower at that index blooms. Okay, so after day one, right, we've seen the first flower bloom, so he puts an X here, or she. After day two, the second flower blooms, we put an X at the end. Day 3, it blooms here, and if we continue this off all the way to day 10, our array would be full of bloomed flowers. Okay? Slightly more complicated example, on day 7, all of these flowers bloom, and on day 12, all of them are bloomed. What do we have to do? Well, we need to return the minimum number of days you need to wait in order to make M bouquets from the garden. If it's impossible, return -1. Possible is pretty easy. If there's not the number of flowers divided by k greater than or equal to m, we can't do it, right? 5 divided by 2 is not greater than or equal to 3, so we can't do it. We can't make 3 bouquets that need 2 flowers each if we only have 5 flowers. Okay, so why is this problem hard? Well, it's hard or harder because if we wait 7 days, right, we can pick sort of maybe this bouquet, but we can't actually pick the second bouquet yet because there's no other adjacent flowers no matter how you slice this. If you pick these 3 or these 3, those are the only 2 sets you could pick, but you can't actually pick a second group of 3 after that. So you have to wait all 12 days to be able to grab these 3 and then maybe these 3 or maybe these 3, right? We have more options on day 12 than just one possible solution, but we have to wait until day 12 to be able to realize all of those solutions. Okay, so let's go into the problem. So I put together a sort of small example to sort of illuminate this problem, hopefully. The main idea that we're going to work off of is a question, actually. And the question I'm going to ask you is, if we remove 100, can you still solve this problem? Well, you might say, yeah, we can just pick these 2 and these 2 and these 2. Or maybe you don't pick those. Maybe you pick these 2 and you say, yeah, 99, right? But that's not actually the answer. So can we keep going? What if we remove 99? Can we still solve the problem? Like, well, yeah, sure, this one. And maybe we change our mind. Maybe we like these 2 or these 2, you know, and then these 2. And we say, okay, well, we need 8 days. Can we do it again? Move 8. Well, we can, maybe we change our minds and constantly, and we decide and we pick that 2, pick these 2, and then we can't make a third, right? We've used 1, we can't use 3, we can't use 7, there's no adjacent flower, so we're kind of stuck. So we realize we actually need 8 days in order to solve this. We need this, something from that, and then our third bouquet. And that's sort of the idea behind the algorithm. The implementation details are a little bit trickier than that because we need to be able to access all of the information that I just described in some fast way. So we need to store 3 major things. The first thing we need to store the number of bouquets we can make given the elements we've dropped. So in this case, when we drop nothing, that's pretty easy, right? It's just the size of the array divided by the number of flowers needed in the bouquets. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9. We can make 4 bouquets with this. And maybe we can make different 4s, but we can only make 4, right? You can't actually make more than 4 bouquets. And so we need some sort of bouquet counter that's going to tell us for any given iteration how many bouquets can we make. For example, if we drop 100, we can still make 4. This, and this, and this, right? Now if we drop 99, how many can we make? Well, we can make 3 now. We can't make 4 anymore, right? But 3 is good enough. And then eventually when we drop 8, we can only make 2, and we realize that when we observe our bouquet counter that goes below M, we realize we must have needed the thing that we just dropped. And if you notice that the thing that I'm doing is I'm dropping them in order, so we have to sort this somehow too, right? We need to take all of these days and we need to sort them. But not only do we need to sort them, we need to remember what index they were at. Okay, so for example, when you sort, you can do that in a few ways. I'll leave the implementation up to you. I chose to pack everything into a list of tuples and then sort the tuples based on the actual day. So for example, we would be sorting some tuples 7, 0, and 8, 1, and 99, 2, and we would be sorting everything based on the center, or based on the first value. And what this is going to allow us to do is remember where we cut things out. So there is a little bit of detail in how we compute bouquet counter. Let us imagine, instead of 1, 1 here, there's a bunch of stuff. Okay, and bouquet counter was n. Maybe we knew this answer. Okay. Can we immediately be able to compute the number of bouquets we can make if we drop 99, given that 100's already dropped? If we drop 99, can we immediately determine how many bouquets we can compute if we started with n? We don't even know what the number is. Can we know how many it is relative to n? Well, I would argue we can, because if we drop 99, the only thing that's going to be affected is some left pointer and right pointer boundaries. If we know the answer of everything with 99, when we drop 99, the number of bouquets going to be changed are going to be dependent on the numbers that are in between other dropped numbers. So for example, before we've dropped 99, we can make 1, 2, 3 bouquets. When we drop 99, however, we can only make 1 and then 2. Or if you like these 2, then 2. So actually the number of bouquets we can make for any given iteration is going to be n, the total number of sort of bouquets that we computed previously, minus, let's assume all of the bouquets get dropped here. So this is going to be 1, 2, 3, 4, 5, 6 divided by 2. Remember, we could have made 3 here. So it's going to be minus 3 in this case. But we need to add back in the bouquets we can make from each split array. So if we have this split and this split, we need to add back in 3 divided by 2 plus, oops, keep the colors the same, plus 2 divided by 2. And the only way we can determine the size of these arrays quickly without needing to iterate all the way through them is by remembering these pointers, the left and right pointer. For example, if we have some array, right? Let's assume we initialize the pointers to -1 and the length of the array. So they're outside of the bounds of the array. In this case, let's say we have 100. Let's say that's index 100 over here. Or let's say it's index 60, just for easier sort of visual purposes. And what we really want to know is when we decide to drop a number, for example 100, let's say that's index 30, because it just happens to be the longest blooming flower, right? Let's say that's index 30. Well, we're going to say, well, we're splitting this array at index 30. So we're going to use binary search, and we're going to insert 30 in log n time into this array. Okay, and there are a few ways to do insertion in constant time, particularly if you store it in the form of an array. You can do insertion in constant time. You can't do it with the linked list, but you can do it with an array. So we'll assume it's an array. So we can find where it needs to be in log n time, and we can insert it in constant time. Now, let's say we drop 99, and that's index 2, 0, 1, 2. We insert 2 into this, and we realize it's here. When we look at, let's imagine there's a bunch of stuff here, and this is index 30. When we insert the 2, we can look at 30 and look at -1 and say, oh, I see. So I have 2 elements here. And so when we compute the distance, the size of this array, we need to remember that these indices are non-inclusive. Okay, so this distance, right, if the distance between A and B is, if A is a point after B, then it's A minus B plus 1. Well, we need to make a slight modification. It has to be 2 minus 1, right? Because we want it to be in between this. So it's going to be 2, minus 1, and then minus -1 plus 1, because we want to be like to the left of it, or to the right of it, excuse me. And then we add 1 at the end. And this is going to, simplify to 2. Okay? So how you compute the size of this array is basically everything in between. And you can immediately update your bouquet counter based on sort of how you're splitting this and how you compute the number of bouquets you can have. And whenever the bouquet counter drops below the number that you need, you just immediately return the last number you dropped, because you need it, right? So that's pretty much all the sort of implementation details. Once again, I don't show the code in these videos, so if you want to see the code, it's in the comments below. If you have any questions, feel free to comment and I will reply, and hope to see you in the next one.